Alright, so it's 2 a.m. right now. I don't know what I'm doing with my life. So I decided to record a video on ozonolysis. I don't know how to pronounce this. I'll be talking about this reaction in depth. That means this video can get a bit advanced. So if you don't know much about organic chemistry and you want to know how this reaction works, this video is perfect for you. So yeah, let's get started. So what is ozonolysis? I suggest that you keep a pen and a paper with you and make notes with me. That would be more beneficial if you want to learn something. If not, then it's completely fine. I cannot do anything about that. So let's see. First off, what is ozonolysis? I don't know. Ozonolysis is a cleavage reaction, and it is also used to oxidate alkenes and alkynes. We'll be talking about alkenes this time. Ozonolysis is also of two types. It is reductive and oxidative. The reagents used for reductive are O3, that is ozone, and zinc with water. For oxidative type, we use ozone and H2O2, that is peroxide, hydrogen peroxide. We can also just use O3 for the oxidative reaction because the axis of oxygen will do the oxidation on its own. So yeah, that's a cool fact, I guess. So what happens in this cleavage reaction? The double bond or triple bond, we'll only talk about the double bond in this video because that's what I know. I'm still in the 12th grade. So the double bond gets broken in this reaction. An alkane is formed, and the alkane is then broken up into two smaller molecules. It is a two-step process. First we add ozone, and then we do its hydrolysis to get the cleaved product, and the cleaved product is either a aldehyde or a ketone. So that's the whole flowchart for you. I hope that I got everything correct and I covered everything. It's not the end of the video. I'll explain a bit more. If I did not, please forgive me. It's 2 a.m. I cannot sleep. My necrophilia, no, not necrophilia, what the fuck, Jesus Christ, not necrophilia, insomnia. My insomnia is killing me, so if I got any of that wrong, please forgive me. I know I didn't because I'm really good at this, but yeah. So let's look at the reaction first. What is ozonolysis or ozonolysis? Alright, so let's take a look at what ozonolysis is. I'll write the reaction first. We usually take an R group which is attached to a carbon which is having a double bond or a triple bond. Again, for this reaction, I'm taking a double bond, and this is attached to a R dash, and we use ozone O3 and zinc with H2O for reductive ozonolysis, or for oxidative ozonolysis we take H2O2, hydrogen peroxide. The final product that we get is this, and yep. Now let's take a look at the mechanism. So I'll explain that to you now. I hope I can do that. Alright, so let's take something for example that has a double bond. Let's take this. Yeah, my YouTube channel, C2H4 ethene. So what happens is when we make it react with ozone, if you don't know what ozone looks like, it looks like this. There are 3 O's for oxygen. This is what it looks like. Since this has 3 bonds, it will have a plus charge, and this only has a single bond, this will have a negative charge. So this is the first step, that is the treatment. Oh my god, why the fuck is my phone going off? Oh, my STD report came back. It's positive. Alright, so when ethene is treated with ozone, or ozone is treated with ethene, what happens is because of I don't know if you know what an inductive effect is, but because of this highly unstable ozone, it resonates, and there is a plus over here, there is a minus over here, and there is no double bond. I won't draw it right now because that will mess up the mechanism. All I want to say is there is a minus del charge here and a plus del charge induced because of this instability. Alright, so what happens because of that? This negative charge reacts with this positive charge, and this negative charge reacts with this positive charge, and so a structure like this is formed. CH2, CH2. There is a oxygen over here. There is a oxygen over here. There is a oxygen over here, and there is a single bond over here. And this, my friends, is called a mono-ozonide. A mono-ozonide. I hope this is how you spell it. This mono-ozonide has 1 and a 2 peroxy bonds, and these are really weak. And it's also a 5-membered cyclic ring, which is also really bad. So what happens is this bond breaks. It gets cleaved. It can either break like this, or it can either break like this. Wait, let me change the color. Or it can break like this. Okay, this oxygen will always be left out, and this is called a cleavage. And I love cleavage. This is then, let's say that I cleaved it along the blue line. So this will become, this oxygen gets this bond, half of it, and this one gets half of that. I don't think that's how it works, but that's how I like to imagine it. So this will have an oxygen like this, and this one will have CH2, this oxygen like this, and this oxygen like this. This will be a negative one since it has only a single bond, and this will be neutral since it has 2 bonds. Since this carbon only has 3 bonds, that is 2 with hydrogen and 1 with oxygen, it has a positive charge, which implies that it is electron deficient. Now this whole thing then reacts to itself. Now what happens is that this oxygen has a lone pair. If you don't know why it has a lone pair, go study chemical bonding. This lecture isn't for you. And there is also an electronegativity difference between this O and this carbon. So there is a negative del over here. That does not look like a del, that looks like my testicles. And a positive del over here. So this is positive, this is negative. What happens is this negative attacks this positive, and this lone pair attacks this positive. And to negate this negative del, the lone pairs over here go attach themselves to the oxygen. Now what happens because of that? I'm glad you asked. It becomes something like this. Carbon over here, oxygen, oxygen here. There are 2H and there is a 2H. Okay, this molecule is called a mono, however you want to pronounce it. I'm Indian, I like to pronounce it like mono-ozonoid. Okay, I'll drop the accent. Mono-ozonoid, NIDE. Yeah, it's called a mono-ozonide. Alright, this is more stable than the mono-ozonide. Why is that? Because it only has a single peroxy linkage instead of 2 peroxy linkages. Yeah, see? That's why. Now, we don't want this. So if we don't want it, we attack it. How do we attack it? I'm glad you asked. We attack it using something called zinc. Zn. Remember when I wrote this? Zinc and H2O. Yeah, I wrote it for a fucking reason, you. Okay. Yeah, this is where it comes in. Now what this zinc Zn does is very smart, but it's also very dangerous. It breaks itself down to Zn2+, its ionic form, and it attacks this oxygen and it breaks it away. The oxygen that is being broken away is called a nascent oxygen, 2-, and then these two react and then they form ZNO. And what happens after that? This oxygen is gone. These two form a bond, and CH2, boom, CH2, boom. And this compound over here is called 1,2 dioxolane. Yeah, that's what it's called. We don't want 1,2 dioxolane. We want aldehyde or a ketone. So what do? We hydrolysis it. We add water to it. All right. Let's add water to it. And when we add water to it, the lone pair will attack here, and we will get double bond over here, and H over here, and H over here. And similarly, we will get another one of this. So basically we have 2 moles of CHO. So this was reductive ozonolysis. If we talk about oxidative ozonolysis, we'll have to go back over here. So let's draw this again. Monoozonoid, oxygen, oxygen, bam. So the last time we had Zn react with it. This time we'll have H2O2 react with it. What will happen is it will get cleaved like this, and something like this will be made. This will be OH, double bond O, and a similar thing with this, a carbon over here, a double bond O, an H over here, and an OH over here. So we have formic acid. Alright, so that was the mechanism for the reaction. If you take a deeper look into this, let me see if I can do this. I can. Let's make it yellow. Okay. Hold on. I don't know how this works. I just downloaded it. I want it to be thick. Alright, an arrow over here. Yup. Another arrow over here. Can you guess what I'm trying to draw? It's a graph. Yeah. You're so smart. Oh my god, you're so smart. You know that I'm drawing a graph? Wow, look at you. This is going to be progress. No, not progress. Progress of the... Oh my goodness. Progress of the reaction. It's gonna go like this. And over here I'm gonna write potential energy. Did you know I was gonna write potential energy? You did? Oh my god, you're so smart. If you don't know why I wrote potential energy, or why there is a change in potential energy during a reaction, atoms or particles of atoms or molecules, they have a kinetic energy. They're moving at really fast rates, like zoom. So let's say this is chlorine. It's a free radical of chlorine. And let's say this is CH4. This is methane. And this has a really fast kinetic energy. And this collides with this. Boom. When it collides with this, basically what happens is there is a CH3 free radical and HCl formed. This is called halogenation of an alkane, but let's not get into that. What I'm trying to say is the kinetic energy goes from really high value to something really low. And since energy cannot be created nor destroyed, this is converted into this thing that was lower is converted into potential energy. And now when this hydrogen is being removed and this chlorine is being bonded with this hydrogen, there is an intermediate structure called the transition state. This transition state has the highest potential energy, and this takes the most time, and this is also called an RDS, which is called a rate determining step. I don't know why I just told you guys that. It is officially 3 AM. I have been doing this shit for fucking 20 minutes now. So it is a 2-step reaction. Well, not 2-3 actually, but I like to call it a 2-step reaction because the first step is monoozonoid, The second step is monoozonoid, and the third step, so let's call it a three-step reaction, all right? The third step is the hydrolysis or the reaction with peroxide. All right, so let's draw the graph. If you know anything about potential energy versus POR graphs, you know that it does not start with a zero. So it starts with some sort of unit over here. I don't know the exact data because I don't know, I'm in 12th grade, I just entered 12th grade. This will be the first RDS where moloozonoid, M-O-L-O, moloozonoid is formed. It looks like a V. Moloozonoid is formed. The second peak will be this transition state where mono, M-O-N-O, monoozonoid is formed. The peak is lower than that of molo because this is way more stable than wait, I drew the thing wrong. This is monoozonoid is way more stable monoozonoid is way more stable than moloozonoid. That's why the peak is lower. There is a delta H over here. And then the third step is the hydrolysis intermediate, or I don't know, the H2PO3, and then the reaction is like this. So 1, 2, 3, 3 transition states. That means a 3-step reaction. And yeah, that was ozonolysis. All right, so what else can okay, this reaction, according to this graph, I don't know if you guys know this word, it's a big boy word. It's called a
Exergonic. Exergonic
reaction. Yeah, it's called an
exergonic
reaction. What else? Oh yeah, this reaction is also used to modify unsaturated fats. UNFs, unsaturated fats. If you did not know, that's cool, right? Yeah, I don't know why I know that. Yeah, I guess that's it for this video. I hope I can sleep after this. If I can't, I'll make another video, I'll upload it. Yeah, thank you for watching, I guess.